Hello everyone, welcome back to another video with Mr. Coder, and in today's video, I'm going to show you how to solve Deforestation, Problem 2 from USACO Silver 2024 December content. So overall, I'd call this the second hardest problem. The first problem was probably the easiest. And the third problem I didn't solve, so I can't really judge that one. But for this problem, I'll be showing you how to solve it. And also, I'll be going a brief explanation on how to solve the subtask, even though I didn't do it. But after thinking that, so you could also solve the subtask as well. If you end up solving question 3, then you can solve the subtask to also pass or get a higher score. So, so for this problem, Farmer John is expanding his farm and he has identified the perfect location in the red-black forest, which consists of N trees which is n is less than or equal to 10 to the fifth, and it's on a number line, with the ith tree being at position x by. So they're from negative 10 to the ninth to 10 to the ninth. So notice that can also be negative. And environmental protection laws restrict which trees Farmer John can cut down to make space for his farm. There are K restrictions, which K is less than or equal to 10 to the fifth, specifying that there must always be at least Ti trees in the line segment L of I to R of I, including the endpoints. So that means it's inclusive. And it is guaranteed that the red-black forest initially satisfies these restrictions. And Farmer John wants to make his farm as big as possible. Please help him compute the maximum number of trees he can cut down while still satisfying all the restrictions. So I'll go over the first example. So for the first example, these are where all the trees are. So I'll make a demonstration a little bit. So if these are the 10 positions, of course there will be more, but those points are insignificant. So 1, 2, 3, 5, 6, 7, 8, 9, 10. So then there's a tree here. There's a tree here because 1, 2, and then there's one at 4. There's one at 6, 7, and 8, and then there's one at 10. So then these are where all the trees are at, and these contain all the important points. And in this segment from 2 to 9, there has to be at least 3 trees. So then when you're looking at this, you notice that you can remove this tree here because you can remove it because it doesn't there's no restrictions on it at all. You can remove this one because there's no restrictions on it. And then for this one, there has to be at least 3 so that you can remove 1 and 2. So then for this next one, you add another restriction as well. So I'll erase the previous X's that I marked. And so here's a tree. So then there's also a restriction from 1 to 10, which is this whole thing, that you have to have at least 1 tree, which doesn't affect the answer because of course the inside has to have 3 trees. So it'll of course be the same as last time. But then this new one is 4. So then you could remove the first tree because you can remove this first tree because of it still qualifies, still satisfies the equation. And then you could remove this next one too because both still satisfy the equation. You can remove this one too. And then there's 3 here, 1 here. And then the key thing to notice from this is it doesn't matter which trees we remove as long as we remove the maximum number because all trees are weighted equally. So removing 1 from the beginning is no different from removing 1 from the end. So notice that, of course, we can't go through all the points. We can't go through all the points because it goes from negative 10 to the ninth to 10 to the ninth, with, of course, 10 test cases. So that'll be like 2 times 10 to the 2 times 10 to the power of 10, which is way too slow. So that wouldn't work on any test case because there's no subtask on it. So I'll explain for this test case. You can just brute force 2 to the power of 16 of which trees you keep, and then you can see if it satisfies. And this nk is less than or equal to 1,000. This one you can this one is just a slower version of the solution, which uses log n, which if you do that as n squared, then it would also work like that. So I'll be explaining the solution. So for this problem, you can think of it as, how did we solve the previous problem? Well, of course, we can notice that some of them don't affect our answer. But as I was saying, like, you can't have them from the start. Or, well, you could have them from the start, which means that you can eliminate them directly. If possible to eliminate, you can eliminate. And then you can go like a sweep line through the important points. So the important points are here. These are the tree points. And also these 2 points are important. 2 and 9 represent start and ends. So this is just like a classic sweep line where you go through. And then start should be before, like if there's any start at the time, it should be before any trees. Then it should be trees. Then the end of the segment should be after, because it's inclusive on both sides. So make sure that you have that in the correct order. And then the next question comes, how do you determine whether you can remove the current one? Since if you can remove the current one, remove it, because it's there, you'll never miss out on any trees, because you if you can remove it now, then it won't hurt later. So, and if you have any proof, you can let me know. But that one, like I kind of just assumed, but for my code here, I first got the input and sorted it. And this is important to sort because then I keep track of like different points. And then I also have the array of restrictions. And then this is my suite, SWP. And then I have different types. So as you see here, this is 2, this is 1, this is 3. This is to help me order it. So then it goes start, tree, end. So type 1 start, type 2 tree, type 3 end. And I also inputted the indexes so I could just reference right back. So I sorted it with a comparator, which was unnecessary because all of them were less than, but I still did it just in case, since it's always good to be safe on these types of competitions, because you never want to have a stupid mistake that you can't find. And that's so frustrating when you just can't find it, and this such a unusual contest, like it happens once a month for 4 months. So just some general strategy. So this is your sweep line. And then you also set up a set, which represents how much, sorry, you have a set that represents how much you can remove. So then if we, and then the map I also have that describes, it's for removing from the set. So then I know what to remove in the set. So this total represents how many I removed in total. And then I go through the sweep line. So then this is the type. So if it's type 1, that's the hardest type, because that's when you have a start. So you need to like figure out how to like insert it. So I'll be doing that after. So of course if it's type 3, that's like the end, so you just remove it from the set. And then I'll go over the start now. So for the start, you start with this and then you go like left, right for you want to see the boundaries. And then you find like the FG and FL, because that represents the maximum tree and the least tree. That's why I sorted this earlier. So then you can find how many trees are in the range. Because in this tree in this multi-set you're trying to find how many you can remove. So you need to find the indexes so you can sum it up. So it would be FL minus FG plus 1, since it's inclusive. And you need to find the max of 0 in this, because of course if there's 0, then it'll mess it up, because I have it as n negative 1. You need to subtract away the start, because this is how many you can this is how many you need to have at least of. So this amount, but make sure you add the total amount you've already removed, because then this is how it makes it efficient, because then you can just subtract, as I'll explain here. And then of course you insert in the multi-set, and then you set it as for the map. And then notice that it's s dot find because it's a multi-set. And then for type equals 2, that's the tree. If the current size is 0, then you can always remove it because there's no restrictions. Otherwise, you get the beginning of the set, which is the least amount, which represents like how many trees you can remove from there. And then if that minus the total number of trees you removed is greater than 0, then you add 1 to the total. And notice that it doesn't matter like if the starting spot is later, because you added the total that isn't included. So this is why it's important to add the total because you subtract it, and this makes it very efficient. So that's why this is n plus k log n plus k time complexity, which is plenty of time. So, and then you just print it out. So as you see, it gets 443. So this problem is just a standard sweep line problem. And the important thing to notice is sweep line isn't the hardest part to come up with, but you need to figure out like how to insert it. So this is probably the hardest part, like figuring out. So you need to subtract the total amount of trees in the range by the total amount of trees that you need to have, which represents how many you can remove, but then add the total. So that this is like the important part to add the total. So yeah, that's how you solve deforestation problem 2 from USACO Silver 2024 December contest. So I also will be posting videos on problem 1 cake game and also how I got a score of 800, which I'll be explaining how I got like subtask as well in a separate video. So be alert for that. So yeah, thank you for watching this video. If you like this video, please like and subscribe, and I'll see you in the next one. Bye.